On September 1st, 1859, an amateur English astronomer, Richard Carrington, was sketching sunspots when he was suddenly blinded by a flash of light. This white light flare was a coronal mass ejection from the sun. It traveled 90 million miles in less than a day, reaching Earth and unleashing a geomagnetic storm across the world.
And the resulting disruption set big waves of electricity down the telegraph system. Basically blew out the telegraph system. Rumor has it might have even electrocuted some telegraph operators. So, it was a big deal.
The northern lights were seen as far south as Cuba. This solar storm became known as the Carrington Event. In the months leading up to the event, astronomers around the world were watching the growing number of sunspots and anticipating a solar maximum in 1860, the following year. Fast forward to current time. Astronomers around the world today are closely monitoring solar activity as we approach our next solar maximum within the next year. Today, I am going off the radar to talk to a scientist that says we are overdue and unprepared for the next major solar storm.
The Carrington level event is something we're basically due for if you look at the statistical timing through history. The bigger one from 14,000 years ago is a total wild card. If something like that happened, then you're talking damage that could last months.
I'm meteorologist Emily Gracie, and you're listening to Off the Radar, a production of the National Weather Desk. On the show, we dig deep into topics about weather, climate, ocean, space, and much more. Our goal is to help you better understand the weather and to love it as much as we do. Today, I'm talking to Dr. Peter Becker, an astrophysicist from George Mason University. Dr. Becker and his team received a $13 million grant this year to work with the Department of the Navy to study this uptick in solar activity that could potentially cause an internet apocalypse, disrupting all electronic communications here on Earth. Now, while I was talking to Dr. Becker, I couldn't help but make some comparisons to the movie Don't Look Up, specifically Leonardo DiCaprio's character. His concerns are legitimate and completely backed up by science, but they're also kind of terrifying. The impacts of a severe solar storm today could be devastating. Here's my conversation with Dr. Pete Becker. Peter Becker, let's talk about the sun. Everybody's been really excited about the sun. It's kind of having a big moment right now with the eclipses and with auroras really ramping up. But there's definitely some concerns here too. And I want to start by getting a little background on you on solar storms. Can you talk about where these storms come from?
Yeah, sure. So the sun is a highly active object. We think of it as just being kind of passive with a nice yellow sunlight and whatnot. But there's a lot of activity going on that you can't detect unless you observe with special instruments. But we see large explosions on the surface of the sun, which basically reflect the magnetic field kind of realigning in a certain way and closing off so that sort of closed magnetic bubbles of matter can fly out into space. Anyway, so there's two steps to that process. We usually see a huge visual flash on the sun, which is what we call the flare itself. And we sort of think of that as the muzzle flash of a cannon, if you will. And then the cannonball that comes out is actually this coronal mass ejection, or CME. And that could be headed in just a random direction. They don't all fly towards Earth. But we can tell when they're going to, because that flare I was talking about, that flash, can form an actual sort of halo around the sun, much like you're looking down the barrel of that cannon. So when that happens, the CME is headed towards Earth. And so it's all about magnetic activity on the sun, which goes through cycles, which are connected with what we're talking about now.
Yeah, so the cycles that you're talking about, what kind of cycle are we in right now?
Right. So the sun has a periodic cycle of about 22 years where its magnetic field actually reverses and the North Pole becomes the South Pole and whatnot. And during that cycle, we see different numbers of sunspots. And these explosions I was talking about a moment ago are actually connected with sunspots, because sunspots are where the magnetic fields are coming out through the surface of the sun. And so that 22-year cycle, we see a ramping up and down of the numbers of sunspots. And when you get near what's called solar maximum, you see a lot of sunspots and a lot of activity. And we're entering now what they call solar cycle 25. So, I mean, there have been lots and lots, millions of solar cycles, but just since humanity has been paying any attention, this is solar cycle 25. And that's going to peak in 2024, 2025, actually. And so the thing about the internet apocalypse is that this is the first time we've seen a significant increase in solar activity since we've developed all the infrastructure associated with the internet. You know, we've had the power grid for a long time and other sorts of systems, and those have been disrupted by previous solar flares and CMEs. But this is the first time we've actually had, you know, the internet-based world economy where the internet's becoming, you know, almost 20% of the global economy. And so the thinking is that we're in a particular sweet spot right now where ramping up solar activity could produce a flare that's large enough to actually impact global internet commerce and communication, as well as power grids.
How does something happening on the sun impact our power grid and our internet?
Right. So it all comes down to, like I said, well, it has to be a large event on the sun. So we have these large solar flares. And then if the CME heads towards Earth and we get a lot of solar particles impacting Earth's magnetosphere, you know, Earth has its own magnetic field too. So first of all, it's not like these solar particles are going to come and sweep across the surface of the Earth and fry everybody. That's not going to happen. Earth's magnetic field is basically going to protect us from the particles themselves. But what happens is there's so much mass in these charged particles that they basically kind of ring the Earth's magnetic field and distort it. And then the Earth's magnetic field, it's almost like dropping a pebble into a pond. There's going to be ripples and waves running around all over the place. And what we know from physics is that when a magnetic field changes or wiggles or you have waves across it, that's going to produce a changing electric field too. And it's actually the electric field that's the name of the game here, because electric fields can accelerate particles. You know, electrons are going to run from a negative to a positive terminal on a battery, for example. So we get these electric fields all over Earth, including on the surface of Earth. And those kinds of fields create large currents. And the currents are the problem, really, because they can be induced in our power lines, also into our internet cables, and all sorts of things. And, you know, any carefully thought out electronic system or electrical system, you don't want anomalous currents running around in there. That's basically a problem. And so that's really the issue. And so we've seen the effect of this in the past. Like, for example, I could talk about an event from 1859, pretty famous event called the Carrington Event. So that's 1859. This is way before the internet, before the telephone, but they did have telegraph. And what actually happened was there was a very large flare, and the CME was directed towards Earth. We saw the flash on the sun and everything. And it got here. Now, they didn't know what it was. They had no connection. There was no concept of solar physics at the time. But the particle struck Earth's magnetic field, and the resulting disruption set big waves of electricity down the telegraph system. Basically blew out the telegraph system. Rumor has it might have even electrocuted some telegraph operators. So, I mean, it was a big deal. And if you think about it, the telegraph, you know, was the internet in 1859, and it was gone for a period of weeks to months because they had to rebuild infrastructure. And the other thing to keep in mind is the telegraph system was pretty big cable, pretty large gauge, you know, wiring running all over the place. And that was taken out by this Carrington event. So then you extrapolate to modern systems with, you know, hair width, you know, fibers, optical fibers, electrical wires all over the place, super sensitive equipment, and all these office buildings with electrical closets on every floor with routers in there. It's just equipment everywhere on telephone poles, cell system. That's all super susceptible to the kind of event that happened in 1859. So, you know, we've seen this in human history, and we know what it did then. So that's the extrapolation, is that we're entering a period of enhanced activity of the sun.
Okay, so you said the Carrington event, you mentioned at the time they didn't know what it was. So how do we know what it was? How do you know that that's what the cause was?
Right. Well, it so happens that the reason they call it the Carrington event was because there's an amateur astronomer named, I think, Richard Carrington in England. And he was observing the sun. He was fascinated by sunspots. So he's observing the sun, and he sees this huge flash. And it's so bright that he actually thought he had disturbed the special filter he was using to block the sun, because, of course, you can't look at the sun through a telescope. Don't ever do that. But he was using a special filter, but the brightening was so strong, he thought he had punctured the filter somehow. So he went outside, and the sun itself actually was noticeably brighter. That's how bright this explosion was. So the CME itself wasn't really directly observed in the sense that, you know, there were no orbital satellites, or we weren't actually tracking the particles in space like we can do today. Well, we're certain that it was a solar flare, that's for sure, because of the brightening that was observed. And there's no doubt that there was a CME associated with it because of the subsequent effects on Earth's magnetic field and the blackout of the telegraph system that happened. So that was kind of an unlucky event in human history. There was one even more recently. There's a famous event in 2003, right around Halloween 2003, which was also a very large event. We saw the flare. The CME headed towards Earth, but it didn't hit Earth directly. It kind of glanced off the edge of Earth. Still caused a lot of power blackouts in the northern hemisphere, very enhanced aurora, which is a nice side effect, the northern lights and all. So that event was about as large as the Carrington event, but we got lucky on that one. It wasn't a direct hit. But, the timescale they estimate for these types of events is about 100 years. It's been about, that is for one to strike Earth, and it's been about 150 years since the Carrington event in 1859. So the thinking is we're due for something like that. And now that the solar activity is ramping up again, there's a lot of concern about that because the internet is basically a very soft infrastructure. It wasn't designed or built to be able to handle a large solar event like that because not really profitable to do that. If you think about it, it might cost 3 or 4, 5, maybe 10 times more to have built a really hard internet in the first place. But the bottom line is all about profit. So, the calculation was that it wasn't really necessary. That may change if there's a large event.
So let's say there is this solar flare. We're going to get a direct hit. How quickly do you know this? And then what does this look like to somebody who's just a normal citizen living their life? What does that day look like to them?
Well, it would start with the big flash, and then once the flash occurs, well, first of all, the flash of light actually takes 8 minutes to reach us. That's just the way the speed of light works. So when we see the flash, it occurred 8 minutes ago on the sun. But that still gives us 18 to 36 hours of warning before these slower particles, big, huge, massive cloud of particles reaches Earth. So we have some time. We can react. So the name of the game right now is actually early warning. We're trying to push our computer models of the sun further forward so that we get more hours. Every hour of warning for a large event is like gold in terms of the infrastructure that you can save. So it starts with things like putting communication satellites in safe mode. They're hovering, not even protected by Earth's magnetosphere necessarily. Some of the communication satellites are way out there. Like maybe if you're talking geosynchronous orbit, that's like 24,000 miles above Earth. Not a lot of magnetic field protection up there. So they're basically on their own. And so they need to be put into safe mode to protect them from this onslaught of particles. On the ground level, it's all about disconnecting transformers from the grid. The grid itself is going to get zapped. We can't do anything about the high tension wires. But they'll survive. But the thing that won't necessarily survive are transformers or other industrial equipment. So you basically unplug stuff from that grid. As a homeowner or consumer, you would unplug computers from the internet and AC power. They'll be safe if they're disconnected. The real concern, I think, is people who are at home using life-maintaining medical equipment, let's say, where there's an issue with maintaining constant power. There could be a real vulnerability there. And another vulnerability is just in terms of data transmission, because modern medical technology, even at home, but also in hospitals, relies on rapid dissemination of real-time data, sometimes between hospitals and remotely located doctors, or you can think of all sorts of scenarios. That all could be brought down. So as I mentioned before, it's not like this plasma is going to sweep over Earth and incinerate people, but there still could be secondary causes of death because of communications failures and power failures.
So how long are we talking that communication or power would be down?
All depends on the size of the event. If it were something like the Carrington event, you're probably talking a matter of days to maybe a week before we can get things back up to speed. The bigger issue is that it's not necessarily limited to something like that. There's historical evidence, geological evidence and biological evidence of much, much larger events happening in the distant past. Like a good example is one from about 14,000 years ago, where we see evidence for an extremely large solar flare, which actually comes from carbon-14 dating of objects that were alive at that time. And so when we look at tree rings in a certain area of France, we can actually see a great enhancement in carbon-14 in a tree ring layer, a petrified tree I'm talking about, that would correspond to about 14,000 years ago. And also there's corroborations from ice core samples from Greenland. All right, so now you're talking an event that hasn't happened since 14,000 years ago, but it was probably about 100 times stronger than the Carrington event from 1859. So it's kind of like earthquake prediction, where bigger earthquakes take a longer time to happen. Smaller ones are more frequent, very difficult to predict, but we know they'll happen and they have a statistical likelihood of happening in a certain time period. So anyway, the Carrington level event is something we're basically due for if you look at the statistical timing through history. The bigger one from 14,000 years ago is a total wild card. If something like that happened, then you're talking damage that could last months, because you're talking about a much more extensive amount of equipment that's been fried. You've got to get people out into the field to actually replace this hardware. And you know how it is after just a thunderstorm on the East Coast. It might take a week to just restart the phone system or power system. And this would be much more widespread than that. So that's why the extrapolations are talking about months. And if we're talking about taking out the internet economy, the economic devastation would be very real. It's estimated that the losses in the U.S. alone would be $10 to $20 billion per day of internet outage. So a large event could even dwarf, let's say, what happened with COVID or something like that in terms of the hit on the U.S. and the global economy.
Okay, so now that everybody's sufficiently scared, let's talk about the solution here. What are you guys working on at George Mason? Because there's a lot of work to be done here when it comes to a warning system, correct?
Yes, that's right. So I have a large grant that's funded by the Navy, and we're actually trying to model all sorts of different aspects of this problem, including fundamental physics of what's happening in the atmosphere of the sun in terms of this magnetic behavior I was talking about at the beginning, and how these loops form and how plasma get ejected into space, with the thinking that if we can see signatures earlier on that we can actually use to predict something that's going to happen, we get more warning. And like I said before, every hour of warning is like gold in terms of additional infrastructure that can be protected. More long-term, you're talking about hardening systems on the Earth, communication systems and power systems. But as I mentioned, that's very expensive. And it's sort of, I think of it as an insurance policy. A lot of people buy insurance, some people don't. It's basically, it's a question about whether you're really going to need it or not. Sometimes it can be very expensive if you want a good benefit. And that's kind of what it comes down to in terms of hardening the internet. It would cost many billions of dollars to do that. There'd be a huge economic payoff, but you need an incentive. And my personal worry is we're not going to get that incentive until there's a pretty large event, which really causes widespread problems. And then all of a sudden it's going to be on everybody's radar, and things will happen, and there'll be a lot of money invested in beefing up infrastructure. And that'll probably be the new gold rush, really, will be everybody under the sun will be getting into figuring out how to make it a stronger system. And of course, the farther in the future this happens, the worse it is, because the fraction of our economy that's dependent on the internet is growing all the time. So yeah, in some sense, the sooner the better it happens, because we can mitigate it more effectively in the future if we act sooner.
I've heard people compare space weather forecasting to Earth weather forecasting 30 years ago. Do you see that same comparison in that way of maybe in 30 years we'll be at that point where we do have better prediction system?
Yeah, that sounds pretty reasonable. There's kind of an interesting connection with artificial intelligence here, which is another topic in the news right now. We look at this data from the sun, we're trying to find patterns that we can use to correlate to previous events, right? And this is a thing called machine learning that's been used, which is basically a fancy way of looking for statistical correlations, patterns that connect with other patterns. It's kind of artificial intelligence, but with guardrails, with a lot of control. But of course, this general artificial intelligence that we're talking about these days is going to raise the level of that tremendously, to the point where you can sort of have a genius, so to speak, a digital genius looking at all this data and really understanding it much faster than a human could, and much beyond this machine learning type idea I'm talking about now. Well, that has pluses and minuses too, because after all, we know from weird things that have happened in the last year that AI can go rogue and can go off in some direction that's really meaningless in terms of providing valuable information. So over-reliance on artificial intelligence in a situation like this, could be good. I think it would. We'd probably still have some guardrails on the type of artificial intelligence I'm talking about now. So would get a big benefit from that. And that may actually turn out to be a game changer in terms of being able to make predictions further in the future that will help us. So maybe even 30 years, maybe sooner than that, we'll have a much better capability for making predictions like this. That might actually start to rival the daily weather forecasting that you mentioned.
Yeah, if people aren't motivated by an internet apocalypse, maybe they're motivated by aurora viewing, maybe tourism And how fun that is.
Exactly. Well, yeah, space tourism could be impacted too, because you don't want to be up there on your $200,000 5 minutes of space flight if something bad is happening.
So what would this mean for the International Space Station?
Yeah, the International Space Station is in low Earth orbit. They say low, quote unquote, Earth orbit. It's about 300 miles above the Earth. So that's actually somewhat protected by Earth's magnetosphere. Having said that, it's not as well protected as on the ground. So you definitely would want to more or less bail out of the International Space Station if something big was coming. And there'd be time to do that because we'd have 18 to 36 hours of warning. And they have a Soyuz parked up there all the time, which is basically a lifeboat that they can use to get out.
Wow. So they would all just bail and it would just be empty for the first time in decades.
Yeah. If something really big enough is coming along, that's exactly what they would do. It's also a big deal if you're on the moon, too, by the way. We're talking about lunar exploration these days, right? You're not going to get back from the moon in 18 to 36 hours. But the idea is dig underground habitats. If you're underground, you're protected. This radiation and whatnot is not going to penetrate a thick layer of lunar soil. So that's the idea there. The bigger worry, I think, is Martian exploration, actually. Because if you're going to Mars, you're going to be in space for years. You're way outside Earth's magnetosphere. If a big solar storm comes and overtakes your spacecraft, you're totally on your own. There's no way to rescue, right? And we're talking, exposure to harmful radiation here. So I don't think that's a solved problem yet. You can't really launch a spacecraft to Mars with lots of lead shielding or something like that because it's so prohibitively expensive to launch something that massive. So they're still working on that. There may be ways to create electromagnetic fields, like kind of artificial magnetic fields that might protect astronauts, but that's a big deal. And then when you get to Mars, also Mars basically doesn't have a magnetic field. So you get there, you're on the surface of Mars, much like the surface of the moon, you're unprotected by magnetic field, got to dig a bunker pretty quick. But that would be preferable anyway, because you'd have better thermal control and whatnot than living on the surface of either the moon or Mars. So one other note is that there's another cycle besides the 22-year magnetic cycle. There's something called the Gleisberg cycle, which is about a 100-year cycle. The reason people are really worried now is that one is ramping up at the same time that we're entering solar cycle 25. So you're getting kind of a double whammy effect. And what we're seeing in terms of solar activity right now is actually ahead of the prediction level. It reminds me a little bit of global warming in that sense. If you look at the way the ice is melting, it's totally disconnected. But my point is that in both cases, the realities turn out to be a little worse than the predictions. So this Gleisberg cycle is kind of supercharging the sun as we're entering solar cycle 25. So yeah, we're definitely in an area of concern in terms of infrastructure damage if there's a large event.
Pete, has anybody compared you to Leonardo DiCaprio in Don't Look Up yet?
No, that hasn't happened.
Well, I'm making the comparison right now. You even kind of look like him.
All right, I'll take that. Thank you.
Do you have anything else you want to add? This is very interesting.
Yeah, I get emails from people asking, what can they do at home? I mean, a lot of people are very concerned about this, especially people with personal medical equipment. It's probably not a major cause of concern. We will have warning. And again, a really large event is very unlikely, just like a very large earthquake. So it's nothing to get hysterical about, but it is something to think about and try to prepare, try to have mitigation measures in place. We will have warning. It's not like it's sort of a nuclear bomb going off or something like that. We'll have warning and there are ways to deal with it. So hopefully the next event will be moderate enough to give us a wake-up call, but not do too much damage. And then we can try to harden our systems a little bit more.
Off the Radar is a production of the National Weather Desk. Make sure you're following the show on Apple Podcasts or Spotify or wherever you listen to your podcasts. New episodes published every Tuesday morning. If you know someone that's interested in heliophysics, that's the study of the sun, please share this episode with them. We'd also love you to rate and review us on Apple Podcasts and Spotify. Let us know what you think of the show, and you can give me some ideas for future episodes. Special thanks to Dr. Peter Becker for his time and expertise today. We wish him and his team the best of luck in their research. I'm meteorologist Emily Gracie. Make it a great day.